Okay, are there any questions?
Our homework.
Yeah.
Part C, it doesn't say like if we do it in just MATLAB or we have to do it in both.
Part C. Which one is that? Second problem?
Yeah, say So do we do it just for MATLAB or we have to?
Produce a graph. Yeah, just use MATLAB.
Okay, and the bonus one, the last one,
Mm-hmm.
that's in MATLAB too.
That's fine, yeah.
So
Yeah.
like the two solutions means it needs to show two different graphs.
Mirror images about the axis.
Either something like M or something, but I don't think that's what you want, right?
Let me explain that. So the differential equation is something like this. Okay, and x is from -1 to +1. Right? So it's a one-dimensional planar geometry in terms of your domain. This is x -1 and +1. This is x. And if this is u, the solution is going to be something like this. Right? For a given value of epsilon and a given value of mu. Now for mu equal to 0, there are, this term drops out. So all you have is just e to the power u. Right? So there are two different solutions. One would be like this, the other one would be something like this. For exactly the same value of epsilon. Now if you take the norm or the average of this profile, U is a temperature, right? So it's average temperature, the area under the integral, and then plot it against epsilon. What you will find is that there is one solution here, another solution there. One has a lower value of the average, the other one has a higher value of the average. Okay. Now if you keep changing your epsilon, you will find behavior like this. Now let's say there's only one. So if you connect this, it's going to be a behavior like that. And there is an analytical solution for that problem, even though it's nonlinear. Somebody was able to transform it and get an analytical solution. This is possible only for mu equal to 0. So if mu is greater than 0, then this behavior goes something like this. So there are actually three solutions that are possible. The lower one, the upper one, and the middle one. If you keep on increasing mu, the solution just becomes something like this. So that there's only one unique solution for every value of epsilon. Okay, so
what we're supposed to do is just for mu equals to 0 or even
the last one is to get two different solutions for some value of epsilon and mu of your choice. Yeah, but they have to be the same value of mu and then the same value of epsilon.
So actually, if you can show that norm large, then that's
if you can show that, that's much better than just finding two solutions, because you're finding the entire solution. We're going to talk about challenges in solving these kinds of problems, and they occur all the time in fluid mechanics. And how do you solve for such branches of solutions later on in some greater detail? So this is kind of a preview of how do I get such solutions just using primitive techniques that I know, using fsolve. So what you need to do is give two different initial guesses maybe. Give an initial guess that's closer to this, and then multiply this by a large number to give it as an initial guess for trying to see whether you can get the other solution or not. Okay, is that clear? That's what I had in mind. Any other questions on that?
Yeah. So the solution is dependent on the initial guess.
No, the solution. Well, yeah, which solution it will converge to depends on the initial guess.
So in COMSOL, it only says initial value in the condition.
Yeah,
Because
yeah.
it's a positive, we are guessing the initial value is the same as this.
Yeah, yeah, that's correct. Yeah, yeah, yeah.
Same thing.
Okay, anything else?
I don't understand the hold on and hold off is. I don't
In
know if-
MATLAB?
Yes, I don't know if the hold on and hold off should be inside the circulation or outside the circulation.
Right. So the way to understand that hold on and off is that it's a on-off switch. Every time it goes through that, it flips it to the other way. If you just have hold, I think if you say hold on, it should turn it on, and hold off should turn it off. But if you just say hold, it'll flip. If it was on, it'll turn it off. If it was off, it'll turn it on. Okay, as it goes through the loop. Okay.
So I think it's just like when you plot, if you keep hold on, then you just make the plot wait and then plot another point.
Yeah.
You hold it off, so hold off should be outside the loop, and hold on should be inside. So every time you hold on for the next point.
Right. Okay, any other questions on anything we have seen so far? Today it's going to be a little bit digging deeper into COMSOL to solve the Navier-Stokes equation. So in the last class, what we did was we looked at the the importance of the proper choice of scale to study a problem. Any problem can be studied on different length scales, and there is often a weak coupling between scales, and if you go from one scale to another scale, the problem may look simpler on a larger scale than on the smaller scale. So the specific example we looked at is talked about continuum postulate and said we are going to look at the computational transport phenomena on a continuum scale, meaning I'm going to define a point that remains large compared to the mathematical limit of delta x going to 0, so that I have enough particles I can talk in a meaningful way what are the average temperatures, average velocities, etc. And we saw that whenever we do that, we fix on certain scale, information from the scales below which are lost have to be provided in the form of a constitutive equation, or what we call the phenomenological model. We saw examples of those: Fick's law of diffusion, Newton's law of viscosity, Fourier's law of heat conduction, etc. for the three transport processes: momentum, heat, and mass transfer. They introduce a material property through their definition of the equation, and those material properties depend on the type of the molecule. And MD can actually help in predicting those material properties, but we can also get them from experiments, and from our point, we are going to assume that they are given, and we're going to look at phenomena occurring on a scale much larger than that. And we quickly reviewed the vector algebra, vector calculus, and developed the so-called Navier-Stokes equation. Okay, so the continuity equation and the momentum equation in a very simple way, but in a very general three-dimensional time-dependent sense. So these two are partial differential equations. There are four unknowns: three velocity components and pressure. If you assume them to be incompressible, the continuity equation becomes del dot V. So it actually doesn't have pressure in it, but pressure is influencing the velocity field that you know from here. Delta P influences V. Okay, and V of course will influence delta P. They are coupled. The four equations are coupled, and solution of that is the CFD algorithm. And towards the end of this course, we will see what are the unique problems that are posed by this kind of a pressure velocity coupling problem. We stop there, but then I have another equation here using similar ideas on energy balance. Instead of momentum balance and mass balance, if you do the energy balance, you get an equation for temperature. Okay, and here again you have del dot V in both two places, and if it is incompressible, they drop out. And for incompressible fluids, this is the form of the energy balance equation, which is very similar to the momentum balance equation. Okay, you have a Lagrangian derivative here, and here you have the same Lagrangian derivative. The property is different. It's only density here. Here it is heat capacity. And then you have a diffusive term on the right-hand side, and you have the same diffusive term on the right-hand side. But you do have gravity, which you don't have an equivalent part in the energy balance equation. But you have a source term that is different, that is the viscous dissipation. Frictional forces are converted into heat, and that term is given by mu times phi of v. So phi of v depends entirely on gradients of the velocities, and it's a positive definite term in the sense it's always greater than 0. And these two equations can be coupled. How are they coupled? Because the expansion for this dv dt contains the velocity. It's an advective derivative. So the velocity will appear in here also. That term is what we call the convection term or advection term. The other one is called the diffusion term. This is where the analogy between fluid mechanics, heat transfer, and mass transfer is strongly similar. That was pointed out by the book by Bird-Stewart and Lightfoot in the 1960s called Transport Phenomena. So where he derives all these equations in great detail. And if you look at the mass transfer equation for a species, this is if you have a mixture of methanol and water, how does the methanol composition change in the flow field? It's governed by a species mass balance equation. Previous one was a total mass balance equation. This is an individual species mass balance equation. So that again has this entire thing that you see in the square brackets is your total derivative, the substantial derivative that you see here. I've just expanded it to show how it looks inside. So you see the velocity here. So the velocity field affects the concentration field. Velocity field affects the temperature field. And this is a diffusive transport. And in a species, you can have a reaction by which materials can appear or disappear. So that is a source term. Now, packages like Fluent and COMSOL treat these extra terms as simply source terms. So there is a source term in a reaction, in a species equation, which is a reaction term. There is a source term, which is a viscous dissipation, but you can also have other source terms. So electric heating, for example, you can have it as a source term. In this one also, we saw that you could have in additional source terms, in addition to rho g, those would be electromagnetic forces, for example, electrokinetic forces, etc. And once we open up COMSOL, we will see the same equations, okay? And we will see how easy it is to set up. The problem is decoupled into one of specifying geometries, boundary conditions, picking the physics from this, and coupling them to study various types of problems. And that's the place where you will learn how to present your own project using these tools. Now, those are the governing equations that allow us to track momentum transfer, heat transfer, and mass transfer of a species in a flow environment with chemical reaction, with thermodynamic equilibrium, etc. They're all kind of superimposed onto these fields. So these equations are valid in a particular domain, so you need to identify what the geometrical nature of your domain is. And that domain is isolated from the surrounding. That means you need to have a boundary. And through these boundaries, you need to specify what kind of interactions are possible between the external and the internal bounded domain. And that's where the initial condition, the boundary conditions come in. So there are many different types of boundary conditions, velocity specifications, forces specifications, etc. So we will see those through specific examples. But here I have listed some of the more common ones. In a finite domain, at the edge, I guess you have kinematic and dynamic boundary conditions. Kinematic boundary conditions would be specifications of velocities. Dynamic would be specification of forces that you apply on the boundary. Normal velocity is typically 0 at a solid surface, and we call that as an impenetrable boundary condition. If I have a solid, if I have a fan blowing air, it cannot go into this. It can go only tangentially touching the surface. And that condition is called impenetrable condition. Even on the tangential direction, the solid is not moving, right? So the fluid next to that wall should stick to it. That's called the no-slip condition, okay? So the tangential velocity on a wall, a stationary wall, is 0, that's no-slip. The normal velocity is 0, that's impenetrable condition. At a fluid-fluid interface, what do you think would happen? Suppose I give you this problem of a fluid droplet that is settling in another liquid. There is liquid oil droplet settling in water, for example. Okay, so I want to predict what the velocity field is in this entire domain as well as inside, and they are immiscible. So there is a clear interface. The question is, Okay, on these walls, I will specify no slip and impenetrable boundary condition. This will be a free surface boundary condition, meaning that there is stress-free boundary condition. There is no velocity, but there is no stress as well. And this droplet is settling, so what should be the velocity at the interface? Will there be a fluid motion? And the intuition tells us that if there is a streamline like this, right, and that applies a tangential stress, so there should be a motion like that. And inside the streamlines may be like this. Okay? So there is no slip still, but what it says is both the fluids are moving at the same velocity. The velocity is not zero anymore, like as in a fixed wall. If it is a rigid sphere that is fixed and then the liquid that is flowing past it, then the velocity will be zero on that surface. But if it's a fluid sphere, the velocity will be continuous. That's all you can say. You don't know what the velocity is. You have to find that as part of the solution. And similarly, you have to say that the stresses are continuous across that interface, the tangential stresses. But you don't know what they are. So impose the condition that the tangential stresses are similar. COMSOL automatically does all these things for you. If you identify the interface as a fluid interface, these conditions are automatically invoked. Yeah.
No sleep boundary, is it happening in reality, or is it just an assumption that we take to make it easier?
That's a good question. Very good question. Do we want to make, we don't want to make an assumption to make life easier if it is unrealistic, right?
No.
So the question is,
close to reality.
How close to reality
Yeah, how
is it?
close is that?
Right. That's a good question. There are examples in nature where that is a bad assumption. But for simple molecules like water, air, small molecules, that's a good assumption. Because what happens is, ultimately, it is a molecular interaction with the wall that we are trying to describe in a macro world. So we need to come up with these boundary conditions, these constitutive laws, to capture whatever information that is lost, right? So at the molecular level, when it hits on that, so its tangential momentum is going to be taken away. It may rebound if it is elastic and go away, but it's not going to slide past it. Okay, so the zero slip condition is a good assumption for such small molecules. But you can have a situation, and it happens in reality, and we can actually ask, how do I test this, right? This hypothesis. Let's take that no slip is a hypothesis. How do we test the hypothesis to see that it is real? That's a very valid question, right? So if I have flow in a pipe, something like this, right? So if the Navier-Stokes equation is right, if the no slip condition is right, then I will predict a velocity profile that looks like this. And I can integrate that, I can know what the flow rate is. And I can put two pressure gauges here and find what P1 and P2 are. So I can develop a relationship between delta P and velocity, assuming this model and assuming no slip condition. And that model tells me that the delta P over length versus Q has a linear relationship like that. Experimentally, we verified that. The theory predicts that. Experimentally, we verify that. That means all the assumptions that have gone into developing that analytical result must be reasonable, right? That's how one way of validating no slip. In fact, when I teach the fundamental fluid mechanics course, I give an assignment on this one. Now let's take and relax this assumption of no slip and put there is a slip condition. So the velocity profile actually looks like this, meaning that there is a slip velocity here. Okay, and you have to write a boundary condition for that. The slip boundary condition is u equal to 0.
Yeah.
So the no slip condition is u equal to 0. The slip condition is something like mu times du dr is equal to beta times u. Okay, so beta is called a slip coefficient. This is a model that is proposed for fluids that have a finite slip. So you take this model and solve that, and you get a profile like that. You integrate that, and you find this graph, and that graph will have different slopes depending on for beta 1, for beta 2, etc. But only when beta is infinity you get U equal to 0. And that's a kind of indirect proof that no slip is valid for most simple fluids. But as I said, for polymeric fluids, if you have CMC solution or polyethylene melt, when you're pumping these through these, one end of the molecule can stick to this, the other end may be freely floating inside. Okay, so it encounters something called a stick-slip phenomena. Polymer solutions typically exhibit that, and those do not obey this kind of a linear relationship with beta equal to infinity, for example. So the way you isolate the system and come up with a reasonable set of boundary conditions is based on our intuitive expectation that needs to be validated against experiment. Yeah, a very good question. Okay, any other questions on this? So the velocities are continuous at the fluid-fluid interface. The stresses are continuous at a fluid-fluid interface. The normal stress is not continuous because of the interfacial tension. Okay? The pressure inside this droplet is going to be greater than the pressure outside as you are traversing across that interface because of the curvature. And that's given by another empirical equation, the phenomenological model, the Young-Laplace equation, that relates the pressure difference across a curved surface through the radius of curvature and the interfacial tension that we saw in one of the models earlier. So all these models, boundary conditions, etc., are made available to us as just a menu choice. So we just have to pick the right option to set up problems of various kinds. Now we understand the equations that govern these fluid mechanical problems or transport phenomena problems, and we need to understand the concept of what kind of solution behavior are possible. Okay, so here I've shown a liquid that enters into a channel and it's flowing in the horizontal direction. So when it enters, the velocity profile is flat everywhere. Okay, but as it goes through that, you'll find that the fluid next to the pipe wall sticks to it, right? So there is a small curvature that develops in the velocity profile, and the flat part is still remaining there in the middle, and this is what is called a boundary layer. And as you go further down, the boundary layer essentially grows, as shown by the dotted line. And once you find that the boundary layer is fully grown, the velocity profile reaches your expected parabolic profile for which you can analytically solve. But in the region where it's called the entrance region, developing length, you cannot solve it analytically. Why? Because the equations are so complicated and you have two velocity components that are non-zero. One is the x component in the axial direction, the other one is y component. How do you know that there is a y component in such a situation? This is where your intuitive thinking about the problem and the math becomes very important, right? So I just told you that the velocity as it enters has only one component in this direction. And then I'm saying in this domain there is a y component velocity. How can you rationalize it? Why would you expect that?
Yeah.
Where is the force that causes the y
The
direction?
wall, the actual wall. So the reduction in speed constantly.
That's the key. The reduction in speed. Like if I integrate this, I will get a flow rate, right? But if I go ahead and integrate this one, that flow rate must be the same. Mass is conserved. Every line, the flow rate must be the same, right? And that means that the velocity here must increase because the velocity here has decreased. And if the velocity here decreased, where did the flow go? Escapes into the upward flow, right? So in solving that part, you need to develop analytically by assuming that both velocity components exist. And in your fluid mechanics course, you would have seen the boundary layer theory. The whole boundary layer theory is about studying what happens in the entrance length. But in a computational environment, you don't worry about it because it automatically captures all those things for you, right? And so that is at entrance length. And the entrance length, intuitively, what do you think it would? How do you think it would vary with viscosity? So consider two different viscosities of fluid, same geometry, same flow. One is honey, the other one is water. Which one will have a larger development length? Now we have a division of opinion. We can debate it. Why do you say it's honey?
So the viscous forces within honey are higher than that in water. So as it's moving through the tube, the development of the boundary layer will be much more earlier than what it would happen in water, because there is an inertia.
So what you are saying is, if I have very viscous fluid, the boundary layer length would be shorter. What are you saying?
I think
For what you said the same thing, I think. For what?
momentum. So the higher viscous term you have in honey would dissipate the or kind of equilibrate the momentum in a shorter distance.
You both are saying the same thing. It sounded like it was different.
Is that like whether in honey or water you get a fully developed profile faster? Is that that's
No. The question is, I give you honey and water, you do the experiment, you tell me which one will have a shorter entrance length. Which one will reach the fully developed state quicker along the length? Yeah. And you are arguing that honey will develop quicker. And you are saying water will take longer, which is the same as saying honey will be shorter. Right? Right? That is the right answer. If you have remember from boundary layer theory, the boundary layer thickness grows as square root of nu, the kinematic viscosity. Okay? So the larger the kinematic viscosity, the faster the growth. And if it grows to the center, it's done. Right? So the growth rate is essentially how fast it grows to the center. And so you can do all these experiments. The problem with computational approach to solving these problems is, as opposed to analytical ones that you will do, analytical one gives you an intuition right away. How, like I can say it goes as square root of nu from analysis. Computationally, you will never get that. You need to do the simulation for maybe 100 fluids with different nu and then discover that relationship by essentially curve fitting, right? But it's very easy to set up. If you have to do it by pencil and paper for boundary layer theory, it may take, at one time it took several years for Blasius to solve. Yeah.
I have a question. Are you going to talk about meshing in the future, or?
Yeah. We're going to demonstrate all of this. We are going to talk about the truncation errors that come from numerics. Remember, in the next second phase of the course, we are talking about the physics and the model equations that go with it, and we will learn how to solve. But in the next phase, when we talk about numerics, we will talk about the errors introduced by discretization. But during that time, we will build meshes. I will talk about different types of meshes, what are the advantages,
I'm
disadvantages.
asking because when I try to solve some problem like this in console, and I wanted to apply meshes that console is providing, like the
Physics-based, yeah.
Physics-based mesh, it applied some triangular meshes at the center and some other shapes near the wall. I want to know the reason why our mesh shape should be different in the center of the channel.
We can try to deduce the algorithms inside, but the state of the software development is such that they take ideas from different places and embed them into the code. And we cannot always have an answer to finer questions like this. Why did it pick this size, or there is an algorithm driving that, underlying that. But
the shape is different. The mesh shape is different.
Right, yeah. So there are some advantages to what you will call structured mesh versus unstructured mesh. We will talk about that. In fact, I will show you what are the differences in terms of how they look topologically, and you will not see until you write a matrix down what impact it has on your structure of the matrix later on, okay, when you do the numerical part. So the second example I have, and I'm going to talk about, illustrate this one also today, is axisymmetric flow. Okay, this is essentially a planar flow in 2 dimensions, and this is axisymmetric flow in 2 dimensions. This is the so-called Taylor-Couette problem. They're all governed by the same Navier-Stokes equation. Okay, but here what you have is 2 concentric cylinders, and the inner cylinder is rotating. In this case, the outer cylinder is also rotating with a differential angular velocity. And how does the velocity profile look inside? This paper was studied by G.I. Taylor, a famous fluid dynamicist, and there are literally thousands of papers since then. He published it in 1927, showing the first transition, hydrodynamic stability, etc. So we will set up the problem in COMSOL, and I hope one of you will pick up the project that I'm going to give on Taylor-Couette problem as well. This is the fascinating structure that Taylor-Couette problem shows. Okay? On the top left-hand side here, you see the most simplest flow. The inner cylinder is rotating, the outer cylinder is stationary, and it is axisymmetric. By axisymmetry, I mean the axis is at the center. Okay? By going around it, I see the same profile. If I take a radial cut and look at what the profile looks like, it will be the same along any radial cut. And that's what makes it an axisymmetric problem. Okay? And that flow is unstable, and when you rotate the inner cylinder faster and faster, the centrifugal force of the fluid near the inner cylinder that wants to throw the particle radially out becomes stronger than the viscous forces that want to keep it there. And then you see these kind of cellular patterns. And Taylor predicted exactly at what rotational speed that will occur by solving the Navier-Stokes equation, and then did experiments to verify that as well. And there is a uniform spacing of these cells. And of course, people since then have come and increased the rotational speed further and further, and you find the axisymmetry is broken, and you get non-axisymmetric modes like this. These are traveling waves, so they will just go around. There are animations on YouTube that you can watch to see how these cellular flows look like. And people have actually computed these kinds of helical vortices that go in one direction on the inside and the other direction on the outside. Okay? Very complicated flows. And eventually the flow will become turbulent. So this problem has served as a model for understanding evolution of turbulence through structured transitions like that. And all of them, the secrets are hidden in Navier-Stokes equation. So we can solve to some extent some of these problems. Yeah. Okay. This is a problem that I'm also preparing as a project problem, which came recently, 1998. The same Couette flow between two cylinders, but they have two different fluids that are immiscible. Okay, so they did experiments in this one. So there is an inner fluid, there is an outer fluid, so that you have a free surface, and along the free surface you will put continuity of velocity, continuity of stress, etc. And they have experiments that show these cells that are forming, and how does the interface deform. For example, here you can see the interface deforming. COMSOL, you can set it up fairly easily to solve problems like these. So the problems very quickly get complicated, from single phase flow to two phase flow to turbulent flow, etc. But we have the framework to study these. Now, another interesting experiment, I'm talking about these things because I'm preparing some of these as project problems for some of you, hopefully. So here you have a cylinder that's filled with a liquid, but dispersed with fine particles, glass beads or some other particles. And they are initially homogeneously distributed. And then you start rotating them. When you start rotating them, the particles segregate like this into bands. Okay? So is this the same as what you see as bands in here? Probably not, right? But what causes this? This still eludes. If you can simulate this, you have a very strong paper, because nobody has been able to simulate this yet. Okay? But experimentally, people have documented this. And that would be a good test of multi-phase flow phenomena that you can model in a rotating cylinder. This was a Nature paper, and what they did was put a slurry of sand and I guess not a slurry, but sand in air. And what they do is they fluidize the bed, that is, they inject air from the bottom, and then they rotate the inner cylinder. Okay? So you can imagine, by looking at these, your imagination is only the limit in terms of coming up with experimental devices for your PhD thesis or whatever. So what they found was that these bands are forming in this situation also. This is now air that is being fluidized, sand that's being fluidized by air, but with an inner rotating cylinder. And these air and the sand arrange themselves in bands like these. Okay? Again, these are experimental work. There's not much of a simulation to validate these things. Some of the students in our group are essentially trying to probe and see whether they can capture some of these phenomena. So far we have seen then progressively complicated flow field that evolves from a single phase to turbulent, and if you put a second phase, the interaction between these two phases forming fairly self-organized structures in some cases, but complicated structures in others. And we are going to build the equations for multi-phase flow from the single phase flow very soon in the next few lectures. So let me stop here the lectures and move to console to show you how to set up the solution to the Navier-Stokes equation with energy equation perhaps. So you are free to suggest ideas as we build, and we will just be improvising. I have no specific agenda of what problem I want to solve, except I want to show you that boundary layer development in a channel flow. So it's my intention to do two problems. One is a planar and the other one is axisymmetric, to show the difference between these two. And you should understand what axisymmetry, what does COMSOL do when we pick axisymmetric model. Okay, so this is the initial screen that you get. So pick the model wizard, and we started with 0D, 1D. I guess we didn't really do 1D axisymmetric, but we're going to go to 2D, and then 2D axisymmetric. And 2D to 3D is conceptually the same. So I'm not even going to talk about 3D because it just takes a lot of time for the simulation, right? So you can learn everything that you need to learn in going from 1D to 2D. So, okay, we have fixed our domain as two-dimensional. And what physics? I'm going to solve laminar flow. So I pick that and say add that physics. So it tells me the dependent variables are u, v, w, and p. So in 2 dimension, I have 3 velocity and pressure field. So, and then I'm going to go to study. I'm going to look at steady state solutions, okay, and I'm done. So this is very different, very same. It's not very different from what we have done before for 0D and 1D, okay. Identify the physics, identify the study, whether it's steady state or dynamic, and then you are presented with this screen where you define the geometry. Now, before you define the geometry, let's see what kind of model equations it has put into this folder called laminar flow. This is the reason why I like COMSOL more than Fluent or any other package, because it ties the model and it shows you the model visually. Okay, so you can see the equations here. Rho u dot del u, that's the advection term on the left hand side. It's steady, so the transient term has been dropped. So the left hand side equation was the Navier-Stokes equation was this. Minus gradient of T plus rho G plus mu del square V with del dot V equal to 0. This is the equation that we develop as for any Newtonian incompressible fluid. These are the two assumptions. Newtonian meaning it's a linear rate of strain relationship, and incompressible means density is constant. That model is a very good model for most fluids, air and water being the most abundant one. It requires us to provide only 2 parameters, the parameters that are lost from the molecular nature to the continuum nature. Those are the density and the viscosity. Gravitational force is known, okay, as a constant for practical purposes on Earth, right? So that equation is valid on Moon, on Saturn, wherever you go. You just have to adjust the appropriate G, right? And if you have the same fluid, it should behave in the same way. So those are the equations that are solved here, right? Rho u dot del u. Because it is steady, we dropped it, and you see rho v, I wrote it as v, right? Equals del dot minus pi plus mu. So this whole term, there is the pressure term and the viscous term. Okay? And then F is any body force. So here you can replace it with rho g if you want, okay? Or you can replace it with anything else. For electrokinetic flows, you can put the appropriate model there. So you can solve microfluidics very easily with electrokinetic flows. And the next equation is the continuity equation. So that is the model. Okay? So what we need to do in this board is define the geometry. For what problem do I want to solve? So I go to the geometry folder. Right now I have nothing there. So I can build a geometry by going into this top geometry folder, and it gives me some primitive geometries that are already built. I can use that to build my more complicated geometry, or I can import it from a CAD. Okay, but I'm going to take this simple one, a rectangle, and then once I select the rectangle, I go to this region, whiteboard, and I can just draw with my mouse a rectangle like that. The moment I draw the rectangle, it tells me what are the dimensions of that rectangle. What is its width, what is its height, depending on how far I stretch the domain. You can come and fix that if you want. If you want the coordinates to be nicely located, for example, I can say position is on the corner, and the corner is 0, 0, and the width is maybe 4, and the height is 0.5. You can also go and fill that and then say build, whichever way that you want. Okay, so build the selected one, and you can center that by clicking on zoom extends. Okay, so what I've done is I've drawn a rectangle, placing its origin at 0, 0 in this corner. You can place it in the center if you want, and then chosen this height as 0.5 and the length as 4. Okay. Meshing, that was the next question, right? So I have defined my geometry, and in this geometry, the model that I have here will be, so it's labeled as domain 1. Okay, so that domain 1 will have these equations applicable to them. So COMSOL is called multi-physics model because you can have different domains and you can have different models in each one of them, and they can be coupled if you want. Okay? They can be coupled to heat transfer or to actually fluid flow as well. Okay, so domain 1 is identified with this particular model, and that domain must have boundaries. Okay, so the next thing I need to look at is what are the boundaries. So there is a default folder that is put as Valve 1. So if I click that, it identifies all 4 regions, the 4 regions that are highlighted in blue as walls. Of course, if I have everywhere wall, nothing is going to happen inside, right? So I need to remove some of them as inlet and outlet boundaries. So I need to add those features. Okay, so if I go to the laminar flow model and right click, it gives me all the options, and there is one option for inlet. So I select inlet, it adds an inlet folder. Okay, then I go and click on that inlet folder. None of them is identified as inlet, but I can go and select this as inlet. Then that is labeled as 1, and so boundary 1 is an inlet. And that inlet I can specify a velocity, inlet flow velocity, right? So I can specify an inlet boundary condition like that. So let me put that as 1. Okay, and then I'm going to pick and see what are the other boundary conditions that are possible. So the learning here comes by doing assignments, playing with COMSOL, and thinking about how others have implemented the appropriate boundary conditions. So if I go back and look at what are the other boundary conditions that are possible, I have wall, of course, inlet, and I have outlet, right? And I have symmetry, I have open boundary, boundary stress. Many options are there at the boundary condition. So let me pick outlet. So nothing is identified as outlet. So I go and click on the right side. Now boundary 4 is identified as an outlet boundary condition. But what is the outlet boundary condition? In Fluent, you won't get a clue because you just check a box, just like you do here. But here it tells you what equation is imposed on the outlet boundary condition. The exit pressure is 0. Okay? And the equation that is imposed, if you check that equation, it expands. This is the equation that is imposed at the outlet. What does that equation tell you? What is this entire term? That is the total stress term, right? This is the PI and this is tau, if you like. Tau has been replaced here with the constitutive equation, but this is the total stress in the normal direction. And if you put P0 equal to 0, that means the total stress is 0. That's the boundary condition that is imposed. Now, outlet boundary condition is always a challenge even in real experiments, imagine that you have a tube and you're pumping fluid from this side at a constant velocity. How does the flow profile look on the outside? It depends on how much of the flow is. Like, you can imagine a garden hose. If you have a full-fledged flow, it's just going to go straight, right, with very high velocity. Start turning it down and down and down. I mean, actually, air may go into it. It may start dripping through the bottom side, right? So what happens at the exit outlet, its impact can propagate a little bit into the domain, but it propagates less and less at higher and higher velocity. So there is a kind of a boundary layer at the exit, the thickness of which depends on the advection velocity. If you are advecting a lot, then you don't have to worry about the outlet boundary condition. And we will see the impact of this in our solution as well. And the remaining two are walls. So if you go and click on the wall, initially all four were identified as wall, right? But then I overrode the first one and the fourth one. So it says overridden, I cannot touch it. And second and three will be by default walls. Yeah.
So outlet condition, can we change the equations, or we have to have that, like the boundary equations in the boundary condition?
If you are using this particular model, you are constrained to use those equations. But there is, remember, COMSOL is a PDE solver. It evolved from PDE toolbox. So there is something called a weak variational formulation for solving these differential equations. If you approach it at that level, you can impose any condition that you want. If you can write down, you can impose it.
The user interface.
Yeah, you need to write some scripts probably for implementing that. Yeah, but most of the commonly used ones are given as an option for you. But if you have a good reason to replace it with something else, you can do that. Yeah. Any questions? Am I going fast or okay? So the boundary conditions, domain is fixed, the equations are fixed. What else do I need to fix? Material properties, because I need to know what fluid is flowing inside, right? So where do I specify that? Here, fluid properties. Okay. So here you can pick the material properties. There is a database of material properties, water, honey, whatever. But there is also a user defined, and you can put any value that you want here. I'm just going to put 1 to illustrate. Here you have for viscosity, non-Newtonian model, power law, Carreau model. I'm going to just put user defined as 1. What am I doing by putting 1? I'm setting this as 1, I'm setting this as 1, I'm setting this as 1. Right? So I'm implicitly defining a Reynolds number. Once I fix all these scales, I can calculate a Reynolds number if I want. And then the way I manipulate the Reynolds number is keeping all of them 1 except viscosity. So I just drop the viscosity by 10 times from 1 to 0.1. I'm increasing the Reynolds number by 10. I increase it by 100, I increase it by 100, right? So I can do that. But you can put any user-defined function to describe the property as a function of temperature, for example. In fact, we will show how to couple that with heat transfer. Okay.
Question came to my mind. When we have heat transfer as well, we know that the density and viscosity is depending on the temperature. Is it going to solve it automatically by itself, or do we have?
Not if you put 1, but if you put something like, say, 2 times temperature square, then it will take that temperature and calculate the density at every cell, at every grid point, because temperature will vary from grid point to grid point, it takes those values. So you can couple it through an expression, that's like a MATLAB expression that you can put in there. Okay, any other questions? Okay, so I've fixed the inlet velocity, I have fixed the density and viscosity. I need to do the mesh now. Okay, so if I pick the mesh option, here I have triangular meshes, or I have something called mapped meshes. Let's see the difference between those. Let me just say build all. So it builds by default this mesh, right? So if you ask a question, I said that it is physics controlled mesh. That was an option that it was again default. I just picked that default option. And the element size is normal. This is truly fuzzy logic. What is normal, right? So they have an algorithm built in which maps this word normal to a certain size. And if you blow it up, for example, you can zoom it in, you will see a structure in this mesh. Okay, they are all triangular meshes, right? But what do you see? You see that the spacing is much smaller. The grid sizes are much smaller near the wall. And also, it should be smaller near the entrance, and you can maybe make it bigger as you go in. They didn't do it here. Why do you think it is closely spaced in this region? Because that's where you have sharp velocity gradients, right? The numerical error comes from approximating the gradients with finite algebraic expressions. Question?
Zoom in one more time. Okay, on the wall.
Zoom in one more time. Yeah.
See?
Ah,
That's what I'm saying.
right, right.
So
Just close to the wall, the shape is different.
Yeah.
In the center, we have triangular, and close to the wall, we have
Yeah.
rectangular shapes.
Yeah, right, yeah. So this is what they call a structured mesh. That is, a structured mesh essentially says that they are all connected in sequence. So I need to know only the coordinate locations. You will understand this when I actually show the discretization process for a differential equation. What you need to do is in building the algebraic equations for differential equations, for each domain or for each cell, you need to know where are the coordinate locations. But you also need to know which one is connected to the next. So if I have a grid like this, I need to not only keep the coordinates of these three elements, but I need to keep the information that this is connected to the neighboring 4 cells. Okay? In this case, I don't need that because it's structured. They're all layered one after the other. So this is called a structured mesh or the mapped mesh. You can choose to have a mapped mesh over the whole domain. But because you gave it the option and it knows it's solving the Navier-Stokes equation, it knows that there is a wall, and so it knows that near a wall there is a boundary layer. So in that region, it puts a mapped boundary condition. And then it makes it transition to the triangular meshes. Why would you want triangular meshes? In this particular case, you don't really need triangular meshes. We can go back and develop a mapped mesh, for example. Okay. So when I click the mapped mesh, I get another folder for mapped mesh. And I'll just say build all and zoom it in. So this is now a mapped mesh. There is a uniform structure, right? So in this case, it will be the most efficient in terms of storing information. All I need is coordinate locations of every grid point. I don't need the connectivity information because I know that this cell is connected to the next one. They are organized in a particular way. But in triangular meshes, I don't have that. So I need to store a connectivity matrix in addition to the coordinate matrix. Okay? So there are 2 pieces of information that you store. But what is the advantage of a triangular mesh? If you have a complicated geometry, try fitting it with this rectangular mesh. It's not possible. Triangular mesh, you can always squeeze it in. Okay, so by default, they have. I don't know the answer to that question. Why 2 cells? Why not 3 cells? Right. So that's driven by algorithm. But why it is a mapped mesh near the boundary is understandable because there is a boundary layer there. Okay.
So my question is, so the model is already assuming that we are solving an equation such that there will be a boundary layer already there before making the mesh itself.
Right, right. So those are the only 2 pieces of information they have. I'm solving Navier-Stokes equation. There is a wall, so there must be a boundary layer near the wall, right? But that may not be true if viscosity is very high. The boundary layer thickness may be so large, I don't need to resolve that. And we will do the simulation for 2 different viscosities, and you will see what happens to the boundary layer. But having a fine mesh in a region where gradients are not large is not, you're doing unnecessary additional work, but it is not going to lead to an error. But using a coarse mesh where you have a fine boundary layer is going to lead you to an incorrect answer. So they are erring on the safe side, saying, if you tell me that Navier-Stokes and a wall, before I know the viscosity, I'm going to put fine grids there, right? the third piece of information that you need is what is the viscosity to decide to what extent I should put fine grids near the wall. Okay, so I've done the mesh. Let me just solve it. So go to the study, right click, compute. So it did it already fast. So I have about 5,800 degrees of freedom. What does that mean? I have as many equations, 5,800 equations. So at every grid point, I will have U. This is a two-dimensional problem, right? I will have U and V and P. So there are 3 equations at every grid point. Okay, and it probably has a number 1,800 elements. Okay, so multiplied by 3, roughly 5,000 equations. But look at what happens to the velocity profile. The outlet condition we specified as kind of a stress-free condition. So it seems to go straight. It seems to be good from this point. What it is plotting is the velocity magnitude, that is square root of u squared plus v squared at every point. And you see that it entered with a uniform velocity. So there is a boundary layer development. The boundary layer is very thick. So it reached a fully developed state in a very, very short time. Why? Because my viscosity is very high. Okay, I really will need very fine boundary layer grid near the walls. Okay, any questions on that? So I'm solving a fairly complicated problem in a matter of minutes. So I'm able to get the u and the v velocity component. I'm able to predict where the entrance length is, and I can do now parametric studies. I can go and change my viscosity, go to the fluid properties, and change it to 0.1. Okay, and what do you think will happen to the boundary development length? Now, if you right-click on it, you have one option here, compute. The one below is update. Okay. What is the difference between those two? When you say update, it uses the previously converged result as the initial guess. Okay, so it already have a good profile, and the only number that has changed is viscosity. So it'll converge much faster than saying start from 0, because the initial condition is still initial values. If you look at it, still u is 0, v is 0, and p is 0. The very first time it started from 0 guesses and it converged to that result, right? So this is the way, the idea of continuation. So you get a converged result, you make an incremental change in a parameter, but just update the solution.
Is there a way we can keep both?
Both solutions?
Like,
Yeah, then you need to do parameter continuation. Maybe I'll show you that later. Okay, I think we discussed this once before. We have to set up a parameter, mu as a continuation parameter, and then say solve for these values of mu, and it solves for every value of mu.
Okay, parametric sweep.
Yeah.
Parametric sweep,
Yeah.
and you get the solution. It keeps the solution for every value. Yeah, that's it. It looks like it didn't change much, right?
So the blue, is that 0? Or?
The blue is 0, and the maximum velocity is about 1.5. Okay, and
More than we introduced. More than what we.
yeah, because the between 0 and 1.5, if you integrate that, it'll be 1.
Yeah.
Right? 1 times 0.5, the inlet velocity was 1 multiplied by this height 0.5. That's your flow rate. And that should be the same no matter the value integrate with this kind of. Now you can generate graphs. I guess I don't know. Do you want to play with plotting by yourself? Because I only seem to struggle when I plot these things. Let's try to figure this out. Okay. So if I want to generate plots, line plots, of how the velocity profile progresses, I take the data and cut line 2D. I have a 2D data, so I'm cutting a line from the 2D data. You select that. And when you select that, it asks you, okay, where do you want to cut the line? So you specify this through these coordinates, okay, by the 2-point method. There are several methods of specifying how to cut the line. You can cut any line, and it will sample the data variation along that line. So what I'm going to do is cut along vertical lines, and maybe one along the horizontal line. Let's do the horizontal line first, or maybe let's do the vertical line because we want to see the carbon first. So the points are given here, right? So one point I want to take is x is 0 and y is 0, which is the lower corner here. The other one is x is 0 and y is 1. Okay, so when I select those points, it tells me on which line I'm going to sample it. I'm going to sample along this line. Okay, so they're given the coordinates like that. It also has a feature for additional parallel lines. If you check that, you can generate a whole series of lines. Okay, so I check this, and then I provide the distances between them. So maybe I specify it as 0.2. And plot. This, pardon me? Distances. Why didn't it work? Range. Okay. Start at 0, step at 0.2, and stop at 4. Oh. I thought I would get a series of lines, but that's not
The
it.
green arrow is on the other direction.
Ah, good point. Why did that happen? 0, 0, 0,
Maybe
1.
because you gave 1 for y. Give it 0.5.
That shouldn't matter. But I think it's using some sort of a right-handed coordinate system. So when I point this, it points this way. So I have to point it this way. Maybe it will flip to the other one. Let me try that. This is how I learn. I never open a manual. Just try it, okay?
0.5.
I want to give point. Oh, sorry. 0.1 is 0, 0. 0.2 is 0.5. No, x is.
No, y1 is 0.5. The one on the top. Yeah, 0.5.
Y 0.5?
0. Yes, you want to just start from the top point, right?
Yeah.
0. And 0. I think the down one is
Y
bigger.
Y is equal to 1 if we outside.
Yeah.
Ah. All right. So now it's going to plot the velocity or any variation of any field variable along these lines. So you can see how it develops. Okay. So then what I want to do is plot. Where is that? Results. 1D line plot. Okay, you select that, and then right click, and then line graph, and in the line graph you select which variable you want to plot. So by default it's U, so just plot that. What happened?
You did not specify the lines.
Ah, there. Really funny plots. Obviously, what does it tell me? The moment I see it, the grid resolution is not good enough. I use the coarse match grid. Right? So I get these piecewise linear function. But eventually, they all collapse on this profile. So the final profile is correct, the parabolic profile. But during the entrance region, there is some sort of inaccurate result. So this one is totally inaccurate. I don't know why that is. Because can you understand why it's 0.5? That's actually a learning moment. The entry point, right. So what happens at that corner, there is a discontinuity in velocity.
X is 0.
X is 0 along one line and 1 along the other line. Right? So this is the entrance. So if I approach this point, so I'm plotting the velocity variation on that particular one. If I approach that point from this side, the velocity is 0. If I approach that point from this side, everywhere the velocity is 1 here. So at the corner, is it 0 or 1? And that you call as a singularity, right? What it does is takes the average, 0.5. So the 0.5 is coming from that fact. So this is the very first line at 0.5. So and that creates a big error everywhere. To isolate that error, to localize that error, what do? You increase the number of grid points in that domain. Okay. So there are a number of other options in the solution. Let's see whether it shows you here. It's taking a long time. My computer is not fast enough. You can see that it's Surface i7 with 16. Surface Pro.
It's still dual core.
Hmm?
It's still dual core.
No, it's i7.
i7U processor. It's a dual core hyper-threaded with four threads.
Uh-huh.
So it's still dual core.
Yeah. So now you can see the mesh is really very, very fine, and I have 90,000 mesh points. Okay, so it's going to take a long time to solve this, but you can see how the boundary looks. Really fine. So you're going to localize that discontinuity effect to very small effect. So you will get accurate results here in this region. Whereas previously, if that was the mesh size, the next point is also going to be an error. Right? So that's how you localize the singularity impact. I don't know whether I should try to solve this. It really did fast. Huh?
Because we
I don't think
updated
it's
it,
all
so
right. Yeah. We just updated the.
I think it's fine because the
Well-
center points were all the same. So it just updated.
Yeah, I didn't update it. Yeah. I think I need to solve it.
So can't we just make it thicker, like finer on the edge? And
You
not-
can. There is another feature called adaptive meshing. So if you enable the adaptive meshing, it actually gets even more sophisticated, and there is a theory to back that. Essentially what adaptive meshing does is, once you get a solution, at least a tentative solution on the initial grid that you give, it calculates the gradient in the domain. And then in those regions where the gradients are high, it puts more grid points, only in those regions. So it's called adaptive meshing. And you specify a global tolerance, and until it meets that tolerance, it will continue to refine that.
Okay, that's done automatically.
That's done automatically once you enable that, yeah.
Is there a manual way to like just we can control whether?
I think there is. That's a good question. I don't know. I haven't used it. Did you see what happened?
Still got the error, but
You still got the error because that value is 0.5, but it is confined to a much narrower domain. Right? But all the others are pretty smooth curves from that point onwards.
So we could just ignore that.
You have to ignore that. Yeah. Or you could, okay, let me ask you this question. Suppose I had input, I'm not going to run this, but I'm going to show you what I can do. So instead of 1, I specify 1 minus y divided by 0.5 square. I don't know whether you can read this. For the inlet velocity profile, previously I had 1. Now I'm saying that it's 1 minus y over 0.5 square. I guess it should be. I'm trying to say that I can put a velocity profile that fits the parabolic profile here. Because the origin is not in the middle, that's not the right expression. But you can figure out what the right expression. If I put that, what would happen? The singularity will go away, right? Because the velocity profile as you approach this, it will be parabolic, right? So it will approach zero both ways, whether you approach from the top or the bottom. But what will happen to the velocity field that you will solve?
The fully developed flow will be earlier, but the magnitude will be whatever is the flow rate initially. So it won't be 1.
What kind of initial velocity? So the bottommost rate is going to be 1, the topmost rate will be 0.
No. This is the wrong expression. Let's figure it out because I don't want you to go with the misleading one. So what I want you to do is put a parabolic profile that I will get as the solution for this. Okay. So if it is a parabolic profile, it's going to be something like a plus by plus cy squared, something like this. So I need to find out a, b, and c in such a way that it gives the parabolic profile. Now b has to be 0 because it's symmetric, right? And then you can find out what a and c are by putting this is 0 at this point and this point. So when you put y equal to 0, you're going to get a as equal to 0, right? And when y is equal to 0.5, c is, it's not right. So I think
you
maybe
need to do a symmetric case where you start the xy axis at the center.
I can do that. I can place the x-axis here, the y-axis here, and then my parabolic quadratic profile will work, right? So if I had it, for example, 0, and this is minus 0.5 and 0.5, okay, then what I wrote will work. Y divided by 0.5 squared is my velocity. So when y is equal to minus 0.5, it's 0, and y is equal to 0.5, it's 0, and in between it's quadratic. And that is the fully developed profile.
We are going to lose the boundary layer.
You will lose the boundary layer. That's the point I wanted to drive, right? It is a fully developed profile, so it will remain as a fully developed profile. And the v velocity will be 0 everywhere. There will be no boundary layer development, right? Can you try this? Sure. Let's just go and change the geometry. That's easier, right? So instead of corner, let's put it at center and build it. So it's going from minus 0.25 to 0.25. Okay? And
You can make the height 1.
you want to make the height 1? It makes it even easier. Right. Right, okay. And then you go to the inlet and replace this by 1 minus y square.
1 minus.
The previous equation was correct.
Pardon me?
The previous equation of divided by 0.5 is correct.
Why did I not make it as 1? Just
So
one?
that's 0.5 at the bottom and 0.5 at the top. So that's how it's 1.
Oh, I see. Okay, you are trying to fix it.
Oh, but the other one was.
That's why you suggested I make, okay. I don't know whether you guys can see it, it's so tiny there, but it's essentially 1 minus, within parentheses, y divided by 0.5 whole square. That goes from minus 0.5 to 0.5.
The color is yellow, but not
It's a warning.
If it is yellow, it's a warning that simply says that the units are not right. Okay, it's not in meter per second. But we can ignore that because we have not been using dimensions anywhere. We're just using in a dimensionless form. Okay, so that's it. And the mesh, it will automatically remesh if I just say go and compute.
That's also very much
Hmm?
because in Fluent you have to remesh it every time.
Yeah, those things are all very elegantly done. If it notices that you have changed something somewhere, it will rebuild. It keeps that flow. See, there you see the fully developed. There is no boundary development. And if you are curious what kind of mesh it used, you can see that. And this, it did rebuild because we changed the geometry, so it has to rebuild the mesh. And if you go to the plot, it may have problems because we changed. Yeah.
Because the arc length is changed.
The arc length is changed, right. Very good observation. So you guys are getting good at it. That's all we need to know, right? So from this point, you can embellish, right? What are the things that you can do? You can complicate the physics, include turbulence, include free surface, put a sphere in the middle and look at what does it do to the flow. You can put, like if you're interested in, that's another project that I have, flow in a branch, for example, a T branch. All I need to do is go to the geometry, pick a second rectangle, and add it like that. Okay, and then change the rectangle height maybe to 1.
So I have a question.
Yeah.
Can COMSOL do something on the scale of like a capillary tube where
Yep. There is a micro.
molecular forces will also be more significant?
That's an area that I have not played with, but there is a module to interface molecular dynamics with continuum mechanics. So it does capillary micron size channels easily with electrokinetic flows. There is a MEMS module, there is a microfluidics module, there is also MD, molecular dynamic simulation module.
Is it atomistic or mesoscale?
No, I think it's, I don't know. I better not answer that question. I don't think it's DFT scale. So here I'm showing how to combine simple elements to make a complicated one, right? So I had one rectangle, another rectangle. Right now the line connecting the joining these is a wall. So I need to open this up. I need to set up a communication if I want to pump fluid through this and then treat it as a T branch. And there is a Boolean operation that you can use to combine, split, merge, etc. I just need to find out where it is in the geometry. Boolean and partitions. So you take union. Oh, I guess I should select both. And now I have one unit, one geometrical entity. Just combine the two. So the interface here will be treated as one that's communicable across this. So there's a flow there, then the flow will also flow past this one. So it's very easy to build networks of pipes, and microfluidics, it's particularly very convenient. You can build complicated microfluidic channels and then solve the flow equations in there. Any questions so far? I wanted to show axis symmetric, but that's going to take more time. So the remaining 5 minutes, maybe I'll show you how to add an additional physics. Okay. So here we have a laminar flow. Suppose I'm interested in looking at heat transfer in this branch. What do I need to do? Just go to physics and add physics. And there is heat transfer in fluids. Add that module. So it adds a folder containing the heat transfer equations. And it does the coupling for you automatically. How does the coupling look? Okay. So, and you will have for heat transfer its own initial values, boundary conditions, etc. Just like we had for the fluid physics model. Similarly, you can go and add turbulence model. It will add that also. And they will all be coupled. But here you can see how the coupling is. For example, if I go into the heat transfer equation, close this. So this is the equation that it is added for the heat transfer module. This is the one that we saw in the notes as well. Rho Cp U times delta Q. That term is the advection term, energy that is carried by the bulk motion. So this velocity, this symbol, will be the same symbol that you will see in the laminar flow model. That's how the coupling is. So that velocity field comes in to evaluate this. So the problems are actually coupled, right? And then delta Q, but Q is given by Fourier law of convection. Okay. So this is substituted there. These are all various source terms. They are default set to 0 perhaps, and you can add. There's electrical heating, etc. Right, so it's that easy to add a second physics. Of course, you need to specify the appropriate boundary conditions on all those boundaries, temperatures or heat flux. So you need to know the transport phenomena well to be able to specify appropriately. Yeah.
So we can like run a flow in the first rectangle and see the temperature profile of a heated distillate.
Yeah.
So do separate. Because one is a fluid flow and one is a
You can have that.
together.
Like if, for example, this is a wall and this is a solid heat block, you're putting a heat in here, right? So you can identify this domain with this equation and this domain with combined equation, for example, because once there is heating, the temperature field will also be affected. This is why they truly call it as a multi-physics, in the sense you can have different domains with different physics. So heat transfer only here, and in this domain you have both fluid mechanics and heat transfer. And they are coupled through a conductive boundary condition at this point. Okay? So what would be the boundary condition at that interface? The flux Q on that interface from the lower part should be the same as the flux on the other side. Continuity of flux, continuity of temperature, right? Just like in the velocity problem, we saw continuity of velocity and continuity of shear stress. You'll have the same thing here. So it's very important to develop these intuitive fields for how to formulate the problem. And that's what I'm trying to achieve in this course, right? So talking about the transport phenomena and talking about formulating in solution, and then later on about the numerical methods as well. If you know a good grasp of computational transport phenomena, it's very easy to learn to use these things. But you've taken probably one course in transport phenomena, so we need to kind of address what are the various possibilities through examples here and there. Okay, any other questions? Okay, so we will stop there, and axisymmetric we will come back to in the next class, and then move on to other concepts of model building. Still, we are not done with turbulence model, multi-phase flow model, etc.
Yeah. I found it. That's what I mean. So that's equation that we inserted, right? So it's not a time dependent. So they need those. Yeah. So then initial
Yeah.
Hello, thank you for lecture. I have a question. So when, for example, in the kitchen tank, when we open the faucet, the water in the northern hemisphere goes in the clockwise.
Yeah.
And in the southern hemisphere is
When it drains in clockwise and counterclockwise.
yes, exactly. And at the center, at the border, what was the name of it?
Equator.
Yeah. You cannot find that if it is clockwise or counterclockwise. So in the experiment that you showed us with the air and sand, and we see a pattern in the sand, and it was wavy. So it is important. Is it important that where exactly you are running this
No,
experiment?
it's not at all important. The reason is the thought is on the geophysical scale, on the scale of the Earth, the Coriolis force is important.
Mm-hmm.
Now, Coriolis force is a force. It's like a centrifugal force. It's a fictitious force that comes from a moving reference frame. Earth is rotating,
Mm-hmm.
right? So if you pose the Navier-Stokes equation in a rotating reference frame, you come up with an additional term that comes simply from coordinate transformation. Just like when you're going from Cartesian to cylindrical coordinates, you come up with centrifugal forces,
Mhm.
because when particles want to go straight, right?
Mhm.
If they're forced to go through a curvature, that means they experience an equivalent force, because it's a rate of change of velocity that's the acceleration. And velocity magnitude may be the same, but the angle is changing,
Yes.
right? So that gives rise to the centrifugal
Yes.
acceleration. In the same way, Coriolis force arises out of putting it in a moving reference frame. And so it's important on the geophysical scale, if you're talking about cyclones and stuff like that, but not on the scale of a faucet draining. So I don't know whether that is really true. Anybody has documented this, saying that it always goes in
Yeah.
one way, in the other way.
Yeah.
Is it?
Yeah.
Where have you seen that?
I think I asked my brother. I was in my country and my brother was in Australia.
Right.
And also I saw a video, and I think the video was on YouTube.
Okay.
I can find it and send it to you.
Okay.
To make sure for myself. And
Yeah.
yeah.
The problem there, I think, is that there are